The Scoop on Scopes. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne, along with a live audience at the Daytona Beach Museum of Arts and Sciences. Telescopes have been around for centuries, shining a light on our place in the universe since the 17th century. How they work is simple. They magnify distant objects by collecting and focusing light. And through that simplicity, they illuminate the complexities of the cosmos. On this episode, we'll unpack the history and technology behind telescopes with a panel of experts who use them every day. We'll explore how this centuries-old tech has evolved to pierce deeper into our universe and farther into our cosmic past. And we'll learn how we can harness the power of telescopes in our own backyard. The Scoop on Scopes. That's ahead on Are We There Yet? Live at the Daytona Beach Museum of Arts and Sciences. So we're here to talk telescopes, and to do that, we've assembled a group of expert telescopers. Is that a word?
Yeah.
Is it now? It is now.
It
Excellent.
is now.
Yep.
I work with words for a living, can you tell? Joining me is Audrey Martin. She is a postdoctoral scholar at the University of Central Florida and the co-host of the podcast Walk About the Galaxy. Audrey, thanks for joining us.
Yeah, thanks for having me.
Terry Oswalt is Associate Dean and Professor at Embry-Riddle Aeronautical University. Terry, good to have you back.
Thank you. It's good to be here.
And Seth Mayo is the Curator of Astronomy at the Lohman Planetarium here at the Daytona Beach Museum of Arts and Sciences. Seth, thanks for having us.
Great to be here as well on our home turf.
Yeah, exactly. Well, we're going to start with you. You get the first question because you are the home team. Can you tell us the history of telescopes briefly?
How much time do I have? So I love this conversation. I love this discussion. Telescopes are a passion of ours, and I'm glad we're talking about this today because it allows us to share the universe with our community in fascinating ways. So let's rewind the clock back to the early 17th century, to 1608. We have a Dutch eyeglass maker named Hans Lippershey, and he was a spectacle maker, and he decided to put, in some fashion, two lenses together, an objective lens and a smaller lens, an eyepiece lens, and put them together in a tube. And when he did so, he could see things farther away. And at the time, it was considered the Dutch perspective glass. And he was actually unsuccessful, interestingly enough, because it was actually the telescope was deemed too simple and too easy to replicate. Interesting, you know. Other Dutch eyeglass makers, he was from a provincial town in Middelburg, Netherlands, and other Dutch eyeglass makers tried to patent this, and unsuccessful as well. But that's probably a good thing, right? Because the telescope then spread from there. And where it spread eventually, just a year later, is to Italy. And in Italy, there's this very astute, very accomplished mathematician. We all know his name by Galileo. Galileo took these plans, and actually it was recorded that he heard the plans, and within a day, built his own telescope. No big deal, right?
No big deal, yeah. Piece of
And
cake.
so he built his own telescope, and at the time, telescopes weren't thought of for use in the sky. It was used for terrestrial reasons, right? So using them to look at things far away on Earth. Think about sailors using them, navigators on ocean-going vessels. The military, actually, Galileo used his telescopes early on to sell them to the military and make a lot of money, all right? And eventually, he presented his kind of revised telescope over in 1609. Through several months, he improved on a design. And as he did so, he presented in front of the Venetian Senate. He was kind of doing his observations from Venice. And they were impressed and gave him a tenureship to the University of Padua nearby. And later that year, in 1609, Galileo decided to point the telescope skyward. And when he did so, it opened up our understanding of the universe. We'd never seen the universe like we did before. Kind of the latter part of 1609, one of the first objects he looked at is an obvious object, and that's the moon, right? It changed our understanding of the universe by seeing things more than our eyes can see. Our eyes can only take in so much light, and think of a telescope like a light bucket, if you will. And that light bucket can allow us to see and take in more of the universe than we could before it, right? Eventually, as you get to the 19th century, it's harder to produce lens-type telescopes, refractors, after a certain size. It gets too unwieldy to make a lens very large. So you start seeing, after 1900 into the 20th century, the biggest telescopes in the world are of the reflector type. And of course, we have the invention of cameras and photographic plates that allow us to record what we're seeing. We have like spectrometers that allow us to decode the light through the telescope. We can also build telescopes to see other wavelengths of light: radio, infrared, microwave, even gamma rays, right? So these different wavelengths can tell us different things about our universe. And in the 20th century, because of the space race, we're not only able to have telescopes on the ground, we can put telescopes in space, like the Hubble Space Telescope, Spitzer, and Chandra. And of course, in the 21st century, we have the James Webb Space Telescope, using infrared light, but using a reflector type devised in the 17th century. And all of these innovations in engineering and astronomy and telescopes can all be traced back to those two small pieces of glass that a Dutch eyeglass maker put together to see things that are far away. And so telescopes, of course, have become the most important tool in astronomy that we have ever seen.
A tool that you use pretty much daily, right? Terry, can you tell me a bit about the work that you do?
What I do personally is mostly involving stellar astronomy. I'm interested in how stars evolve and age, just like people. They get less active as they get older. In particular, we're using the telescopes at Arizona, Chile, and La Palma and the Canary Islands that Embry-Riddle operates to remotely access the sky. In La Palma, being 5 hours ahead of us, you can start observing at around 2 o'clock in the afternoon, our time. My main interest is learning about the age of the galaxy, and stars called white dwarfs are the skeletons of previous generations of stars, as the sun will be someday, that tell us, like cooling charcoal briquettes, how old they are by the temperature. Their temperatures simply fade with age like a cooling charcoal briquette. So you tell me the temperature, which is related to the color, and I'll tell you the age. And if you find the oldest, coolest, faintest white dwarf, that is the first generation of stars formed in the galaxy, and it tells us the age of the galaxy. And one other project that we're working on right now with about a dozen students is using the TESS, the Transiting Exoplanet Survey satellite that NASA operates, and our suite of 1-meter class telescopes in 3 continents, and the Kepler mission data to monitor stars' activity levels, their rotation rates and their flare rates, how often they brighten. Did you know that some stars, like the sun, brighten by a factor of 100 or 1,000 in as little as 20 minutes? Lord knows what would happen to us if our sun did that. So what we're trying to do is to observe thousands of stars with these facilities in ground and space-based and figure out with what kind of frequency stars burp and make flares. And that tells us something about the behavior of our sun over time. One last comment would be, why is that important? Well, it's scary to think the sun might burp 100 times brighter than it normally is. It hasn't in recorded history, or we wouldn't be here. But in 1859, the sun brightened enough to knock out all the telegraph wires in the United States. If that were to happen, the so-called Carrington event, that were to happen today, all of our satellites, GPS systems, and much of the electrical industry would be wiped out. So we do need to know whether our sun is normal or not.
So well, this was supposed to be a fun conversation.
That's intro astronomy. You now all have at least a B in this course.
Yeah. Audrey, I'm going to turn to you because as Seth and Terry both alluded to, telescopes aren't just here on the ground. They're up in space, right? Let's talk about the James Webb Space Telescope.
A lot of the stuff that we know about the solar system has come from telescopes on the ground, but there are a lot of barriers to seeing light from the very distant reaches of our solar system when there's an atmosphere in the way, when the heat from the Earth itself is obstructing our views in certain wavelength regions. So with space-based telescopes, we can not only look a lot further and see other stars and other star systems, but we can see the detail within our own solar system. We've only flown past some of these outer solar system objects once with the Voyager missions, and hopefully there will be another NASA mission that can go out to the Uranian system and we can study the really interesting and weird satellites that orbit Uranus, and also study Uranus as well. Mm-hmm. But my research is on asteroids. I do spectroscopy in particular, and a lot of the space telescopes take really cool pictures, and I'm sure you all have seen the amazing images from Hubble They look
Very
like
pretty.
lines.
Yeah, very pretty squiggles.
And they have a lot of really cool information in them. So in the wavelength region that I like to work in is in the thermal. Everything has a temperature because, things are moving around. And there are photons that are exactly correlated to the frequency of the movements. And when you can look at an asteroid, the photons that are coming off from the frequency of the movements of the minerals that are on the surface, then we can understand a little bit more about that asteroid's history, where it came from, what it went through, maybe how it got to where it is. The asteroids that I like to study are called Trojan asteroids, and they're out in orbit with Jupiter. They don't orbit Jupiter because they're asteroids, so asteroids orbit the sun, but they're locked in what are called Lagrange points. And so as Jupiter orbits the sun, there's a swarm of asteroids just ahead of Jupiter, and there's a swarm of asteroids behind Jupiter, and they orbit with Jupiter around the sun. And these objects are weird. They're really, really, really dark. They have super low albedos. If you imagine holding a piece of coal, they're darker than that. So if we look at the reflected light, they don't really reflect that much light. So we have to look at the light that's being emitted. That's that thermal energy. And with JWST, I got some observing time during the first cycle and was able to look at some of these asteroids, these Trojan asteroids. And what we were able to find is that not only can we see the individual jiggling motions of the minerals that are on the surface, minerals like olivines and pyroxenes that are minerals that we have on Earth, but because of the shape of their spectra, we can determine the structure of the regolith, the very fine particulate material that's on the surface of these asteroids. And it turns out they're really fluffy. They're like just super, super fluffy objects, which is strange. We don't necessarily expect those asteroids to be fluffy, but that's what we found, and we were able to determine that with spectra, with the spectroscopy from the James Webb Space Telescope.
I'm now imagining fluffy asteroids as opposed to Terry's heat death of our planet. So.
It's a little bit more comforting, yeah.
It is more comforting.
One of my colleagues takes the phrase, "A picture is worth 1,000 words," to the next level. A spectrum is worth 1,000 pictures.
Yeah,
Oh,
very cool.
absolutely.
Yeah, I like that. Terry, we're going to zoom back onto Earth here, and Embry-Riddle, as you mentioned, runs a collection of telescopes, including these at Kitt Peak. First of all, I would like to be a telescope because that looks like a beautiful place to work. Yeah.
That's our telescope to the right of center.
Okay, very cool. So what makes this one different than Audrey's JWST telescope?
It's ours.
Yeah.
We get all the time we want on it. And it's accessible over the internet, and we can take students out to Kitt Peak National Observatory on internships where they learn firsthand how telescopes and instrumentation really work. And that gives them the leg up when they do become professionals to write competitive proposals for the bigger telescopes.
Still to come, the scoop on scopes. Our conversation continues at the Daytona Beach Museum of Arts and Sciences. That's ahead on Are We There Yet? You're listening to Are We There Yet? I'm Brendan Byrne. Our conversation with a live audience continues at the Daytona Beach Museum of Arts and Sciences. The Scoop on Scope event explores the world of telescopes with our panel, Audrey Martin, a postdoctoral scholar at the University of Central Florida and co-host of the podcast Walk About the Galaxy, Terry Oswalt, the Associate Dean and Professor at Embry-Riddle Aeronautical University, and Seth Mayo, the Curator of Astronomy at the Lohman Planetarium here at the Daytona Beach Museum of Arts and Sciences. Here's part of that conversation now.
And just so you know, the JWST is a biggish telescope, but there are over a dozen way bigger telescopes on the ground. And some of those telescopes are able to get very close to the same resolution as the JWST. There's always going to be need for both ground and space-based telescopes and telescopes of all different sizes. because there's always a need, for example, different size vehicles on the roads, semis and compact cars. There's a need for different purposes. And astronomy covers all the bases that require all the different sizes of telescopes. So anyway, the telescopes at Kitt Peak are the ones that we physically go to fairly often. The telescope in Chile is a similar sized telescope at Cerro Tololo Inter-American Observatory. Both of these sites are operated by the National Science Foundation, and each site has 2 or 3 dozen telescopes on the mountaintop. And we also have a telescope in La Palma off the coast of Morocco in the Canary Islands, which is 5 hours, like I said, ahead of us, so that we can use some of those for classes in the afternoon. That is a complement to the space-based telescopes that we write competitive times for, because you're only going to get a very limited amount of time on the largest telescopes and the space-based telescopes, and you're going to want to follow them up. Better yet, you're going to want to do a pilot study to prove that certain objects are worth trying to get space-based observations. So you've got a before and an after need for the ground-based telescopes. The space-based telescopes can't be on the same target for a long time. You can from the ground, especially when you have your own telescopes.
And sometimes there's telescopes in between, right? Terry, you and I got to ride on this thing, didn't we?
Yeah, we had a good night that night. It was before COVID. The NASA Stratospheric Observatory for Infrared Astronomy, a Boeing 737 SP extended cabins and stripped on the inside to make it as light as possible, is home to a 2.5 meter telescope. That's 2.5 meters is approximately 15 feet in size. Huge, even by ground-based telescope standards, except this one flies up to 46,000 feet above the highest airline altitudes, where you're more than 95% above the atmosphere and all of the water vapor is below you. The water vapor is what hides the infrared signatures of things like asteroids that you want to observe. And since Sophia was able to fly at an altitude that allows you to do infrared astronomy, you could do research that doesn't involve having to launch a spacecraft. It's a sweet spot in the expense category between a large ground-based telescope and a large space-based telescope was this particular aircraft. Mm-hmm. Unfortunately, every space mission, and this was considered by NASA to be a space mission, goes through what's called a senior review cycle every 5 years. And in astronomy, we have what's called a decadal survey, and 2020 is the current survey that we're subscribed to. All the funding agencies refer to that when they decide what they're going to fund. And poor Sophia was decided that after 12 years, enough is enough. We have to cut the budget. So now if you want to see Sophia, you'll have to go to Tucson, Arizona, out to the Pima Aircraft Museum. We had the opportunity to do the only mission that Sophia ever flew out to the east coast of Florida. And on that particular night, the two of us, along with a team of 20 or so people.
I wasn't helpful at all. I was just.
Well, there's a picture of you interviewing the flight technician.
I was working.
There. Yeah. That's Brendan right there on the left of the. We went out to observe the occultation of Triton. That's one of Neptune's moons. Mm-hmm. It's the biggest moon that Neptune has, and it passed in front of a star on that night, but you had to be in the middle of the Atlantic Ocean to see this 30 or 40-second event. So we all flew out there and measured the rate at which the light dropped as Triton passed in front of a background star. Long story short, if it were just a rock occulting the star, that's the proper term for something covering up a star, the light would just drop instantly and then come back instantly. But because it was a gradual drop and a gradual reemergence, you were probing the atmosphere of Triton. It's a big enough moon that it does have an atmosphere, and those observations showed that Triton's atmosphere, because Neptune and its moon Triton are moving away from the sun in their egg-shaped orbit, are becoming winterized, and the atmosphere is freezing out like snow. So the atmosphere was shown to be getting thinner by these observations.
Let me tell you, that was the most difficult assignment to get cleared because I had to tell my boss, yes, I want to go fly in an airplane with a big hole in the back of it through the Bermuda Triangle.
Yeah.
Yeah. So, but we made it
oh,
happen.
by the way, pride and joy, the senior pilot was an Embry-Riddle graduate.
Yeah.
So.
And I got to press the button to open the door.
Yeah.
Did you get to do that? That was fun.
Got to ride in
That
the
was fun.
cockpit,
yeah,
too,
it was
by
cool.
the way.
It was cool. It was a good time. I want to talk to you all about how telescopes can be inspirational, right? This is an image that I have loved even before my job. I grew up looking at the Hubble version of it, and now JWST brought us this beautiful picture of the pillars of creation. Not only is it gorgeous, but this is where stars are born. And it's very inspirational and cool and all that. Seth, the last time we had you on the show, we talked about the art of these telescopes. For people who aren't scientists and who are just here to take in the beauty of the universe, how important are telescopes in telling the cosmic story of us?
So you bring up the pillars of creation here on the screen, and it is one of my favorite objects to talk about. When you look at it, how can you not wonder about what's going on there, right? To me, and this is just sort of the human in me here thinking about this, they look like giant claws in space, right? Big space fingers, I always kind of describe them as, right? And you see this picture is a great side-by-side comparison of Hubble's version using mostly visible light, and then on the right side is the James Webb version using infrared light. And you can see the differences, how infrared light can help you pierce through the gas and dust and see more. And you can see that difference right there. Plain and simple, you'll notice how the left side with the Hubble version has these very more opaque dust clouds, right? And on the right side with Webb, you see the stars behind it. And what it's showing you, it's just giving you a little sneak peek at star formation, right? And that's why we call these the pillars of creation, right? These are big pillars of gas and dust. That's what a nebula is. And these pillars, they have little knots of gas that are condensing down. And because of gravity, and as it condenses down, it heats up, and fusion occurs, and then eventually a star, eventually pops out of that. And Webb is showing us that in amazing ways. And actually, in the Webb version of the image, you'll see little red dots around these huge columns, and those are some of those stars born out of that gas and dust. What I also sometimes find with the Webb version of the image, kind of near the bottom, if you want to call it bottom, because I know there's no up and down in space, but for our purposes, it's the bottom. There's this kind of feature where it almost looks like a Godzilla kind of creature, shooting fire out in one section of it. It's an amazing feature. And we had an exhibit here in 2023 at the museum here, and I had a chance to curate called Unfolding the Universe, and it was about the James Webb Space Telescope. And we printed these images large format, right? Really, really big. And we printed the pillars of creation up to about 5 foot by 10 foot, all right? Allows you to walk up close to it. And when I used to do tours through our exhibit, I would stop at pillars and I would have to yank myself away from it. I would spend too much time because I would cool. just dig into these huge pillars of gas that have this kind of rough-like appearance to them, and it's just beautiful as well, right? So when you understand how these beautiful structures can allow for stars to be born, and not only stars, there's evidence that there's little pockets of gas and dust that can form into planetary systems around those stars. It really makes you think about how this plays out all throughout the universe and how beautiful the universe is. Mm-hmm. And the coloration, too. A lot of times the colors are added because of filters that are utilized on Webb. And these pictures start off as black and white, monotone color, and the cameras are built that way. And then you add color, and a scientist has to come in and kind of help determine what color goes where. And it's not just for show. It helps to accentuate these objects. Sometimes the color also tells you what element you're looking at, too, so it helps you build this better picture. And when we look at this, we understand where we are in the universe or how we've come to be. Our sun was born in a nebula, including the planet Earth, including the stuff in our body. We are made of star stuff, as we like to say sometimes. And this proves it when we look at this beautiful image. And it is definitely a great combination of this beautiful work of art, but also an immensely important scientific observation by the James Webb Space Telescope.
Audrey, the group that is here, that is joining us, they're going to get to go and look at some telescopes tonight, thanks to Daytona Beach Museum of Arts and Sciences. I remember the first time I looked through a telescope as an adult. It took me this long to see the rings of Saturn for the first time. It was incredible.
Nice.
Can you recall the first time you looked through a telescope and how that has shaped you into becoming the scientist that you are today?
Yeah, the first time I looked through a telescope, I think I was 18 or 19, and I knew I liked astronomy, so I just went out and I bought a 6-inch reflector telescope, and I got the telescope, kind of put it together, and pointed it at Jupiter, and I saw the Galilean moons, and it changed my brain chemistry. It was incredible. They're in a line, you can see them at the angle, and you can Google them and say, okay, that's what they should look like, but then looking in the telescope, the light that is being reflected off of those objects all the way out there at Jupiter traveled from Jupiter all the way into my eyeball. It was crazy, and it really highlighted the humbling experience it is to study and just think about astronomy. It's so little. Space is so big, and it's so little, and we're little too. And so it can help when you're having a rough day to think like, I'm just a little person on a little rock out in the little solar system. Yeah, it was amazing. It was incredible.
That could get wiped out with one solar burp, right?
Yep, exactly. Yeah.
One thing I sometimes do kind of ties into that story is sometimes when we show Saturn for the first time to folks through a telescope, it's so surreal to see.
It doesn't look real.
It doesn't look real. People don't believe me. They actually think I'm dangling like a toy Saturn in front of the telescope because it looks so surreal. And that's the moment that you've captured them, that little spark, right? And it leads to so much more. And so it kind of ties into, Audrey, your same story of seeing these things for yourself. There's nothing like it.
And you have the opportunity to go over to Embry-Riddle and look at their telescopes and also see their larger telescopes in action tonight, right?
Yeah, the largest telescope in the southeast is just a mile or so from here.
And you can climb into it. You can walk up. You can walk up into it, right?
Yeah,
It's
that's
very
right.
cool. Yeah.
That's right.
Well, that's all the time we have today. I want to thank our guest, Audrey Martin. She's a postdoctoral scholar at the University of Central Florida and the co-host of the podcast Walk About the Galaxy. Terry Oswald is Associate Dean and Professor at Embry-Riddle Aeronautical University. And Seth Mayo, Planetarium Director and Curator of Science at the Loman Planetarium here at the Daytona Beach Museum of Art and Sciences. And thank you, the live audience here at the Daytona Beach Museum of Arts and Sciences. Are We There? It is a production of Central Florida Public Media. Our producer is Marion Summerall. Our engineers for this episode are TJ Barnes and Mac Dula. Our intern is Allison Castillo. Editorial guidance comes from LaToya Dennis. I'm Brendan Byrne. Thanks for listening.